Here is another example of applying the central limit theorem. Suppose that IQ scores have a mean of 100 and a standard deviation of 15. What is the probability that the mean IQ of the sample of IQ scores would differ from the population mean by more than 3 if 50 IQ scores are sampled at random? So this is a probability question regarding a sample mean. So given that our random variable is x bar, and because n is at least 30, we can use the central limit theorem. So what the central limit theorem says is that x bar will be normally distributed with a mean equal to the original population mean and a standard deviation equal to the original standard deviation divided by the square root of n. So how x bar bounces around the mean is a lot tighter than that of the population distribution of individual values. All right, so because we want this difference to be more than 3 from the mean, we're actually finding the probability x bar is less than 97 because more than 3, going to, on the left side, 100 minus 3 is 97, so that would be a difference more than 3, any x bar value below 97. Or a probability x bar is greater than 103, so that would be a difference greater than 3 on the upper side. All right, so if we had a less than case, we would have x bar in the middle and we'd have 2 endpoints, but we have an OR case here. So shading the area or probability in question, I'm going to need the mean. Okay, the mean is the same as the original population, so that's going to be 100. I should have included that, so I'll squeeze that in up here. And our standard deviation is going to be 15 over the square root of 50. Okay, we can get a decimal approximation there if you want. I like to put in that whole expression into my calculator. Either way should be fine if you carry out your decimal approximation at least 3 decimal places. All right, so I have less than 97, so we're below the mean. Now this bell curve might actually be tighter about the mean because of this small standard deviation, but this is just a visual aid. So we're looking for this area, whatever this is, and then at 103 or above, this one. And then I want to add these two together. OR means to add, and I have 2 mutually exclusive situations. So there's a couple ways to do this. I could use my normal CDF function twice and have this as my upper bound for the first time, and then have this as my lower bound for the second time using the normal CDF function. Or I could recognize the fact that the total area under this curve is 1 or 100%. So I can use my calculator once, find this area. This is my lower bound, this is my upper bound, and then subtract that from 1, and that's going to give me the complementary area. Okay, or you can use the z-table once here, convert this to a z-score, and then add it to the area you find here, converting this to a z-score. But in this case, you're going to have to subtract from 1 because the z-table reads cumulatively. All right, so going to my normal CDF menu. Oops. And I have a lower bound of 97, upper bound of 103, mu is 100, and sigma is 15 divided by the square root of, what is my sample size? I just forgot, sorry, 50. Okay, so this area between the two shaded areas, rounded to 3 decimal places, is 0.843. Okay, but that's not the area I'm looking for. I'm actually looking for these shaded tail areas. So that's going to be the complement to that. So I'm going to subtract that answer from 1. Okay, so rounding to 3 decimal places, this is going to be 0.157. Okay, so half of this amount of area is shaded in the upper tail, and half of this area is shaded in the lower tail. Okay, so I did not draw this proportionally correct, but that's okay. I'm just using this as a visual aid to help me figure out exactly what my lower bound and my upper bound is and so on.